That's all right. I'll just record it and make them look at it after. I don't think it matters. So, yeah, so the homework this week's about the spinol decomposition. Let's see. So homework, I didn't finish grading the other homework, like the 6 homework. I don't know why. I get caught up with things and it kind of didn't finish it. But anyway, this is the homework. It's about this spinol decomposition. So you end up with this kind of network structure, like 7. They're making dental implants and they want to have this sponge structure. And the spinol structure is pretty good for that. So they do this in a Nature paper also. So it's like they're doing machine learning to get this structure, to figure out how to make it. So it's kind of like machine learning, artificial intelligence to get spinodal structure. It's a little bit of a weird mix, but basically introduces you to the idea of machine learning and kind of how they use it to do materials problems. So, and then it's also dealing with spinal decomposition, which is the thing I wanted to cover this week. Anyway, so let's see, slide 11 is what we're looking for here. So yeah, he goes through in the book, he's going through this. So he goes through this idea of like a chemical reaction where you're going from A to B. And then this extent of reaction idea of the conversion from one state to the other. So an example of that is this cyclohexanes. It's like 3 carbon atoms. It's not a planar molecule. So benzene is when you have double bonds. So there's double bonds, single, double. That's called conjugated. That's always a planar. So benzene or polystyrene, the side thing, is always a planar structure. But when you're missing the double bonds, and these are 109-degree carbons, a tetrahedral, so it has to be 109 degrees. And when you put carbons together in a 6-member ring, they have to form this kind of bent thing. So there's 2 forms that it can have. One looks kind of like a chair, like a lounge, like a Adirondack chair or something, like where you have the feet part goes here and the head part goes there. So that sticks up, this sticks down. So they call it the chair conformation. And that's the most stable. It's got the lowest. This is the free energy. It's got the lowest free energy. And the other, what they talk about that it could form is that thing could pop up and then you'd have what they call the boat conformation. It kind of looks like a boat. But the boat isn't really stable. So it actually forms this kind of twisted boat form. Anyway, it's still a metastable. So that's unstable, and these are metastable. So actual boat is like a twisted boat. The chair is a real chair. So to get from the chair to the boat, the molecule has to twist. And it takes a certain energy to go through that twist. This is like an A to B, like kind of what he's talking about in the book is an A to B transition. And then you have the reaction coordinate would be like how much chair or how much boat it has. So the transition between A and B, right? So that the coordinate isn't actually like a spatial coordinate and it's not a temperature coordinate. It's just like a conformational coordinate. And so there's no chemical reaction. The thing just bends differently. Here it's got a higher energy than there. So if you plot temperature here, so you say like room temperature is like energy in terms of kilojoule per mole would be 2.5. So you could plot like 2.5 on this. So these are the energies relative to the chair conformation. So 2.5 is a low number on this. So you get almost all chair. And if you raise the energy, if you raise the temperature to 1,000 Kelvin, then you end up with 30% boat. You get a split between these 2 things. So there's an equilibrium between them that depends on the energy. So this delta G, delta energy between the chair and the boat, exponential of that over KT is going to decide the percent boat or chair that you have, like a Boltzmann probability for the two. So he's kind of written that out in terms of the chemical potential. This is in the book, you know, the chemical potential of the two states, the number in the states gives you the total energy, then why it would form one state or the other according to that, a thing called the affinity, which is the difference between the chemical potential of the two states. So those chemical potentials depend on temperature. This is basically the kind of the Hildebrand equation for each of the two states written out, the derivative of the Hildebrand with respect to the number of moles of A or B. So the chemical potential is a function of the temperature. So anyway, so this, I don't think that doesn't, all right, this is pretty commonly referred to in the literature, but basically it's not in the book. It doesn't really lead anywhere. Like it doesn't get you, like he just leaves it at that. I mean, he talks about you could do so you could write a Taylor series expansion in terms of this extent of the reaction coordinate, this or reaction coordinate, that thing. But basically that reaction coordinate could be like temperature, pressure. Yeah, I'm not sure what M is here, but basically temperature, pressure, and reaction coordinate. And then you can come up with these terms to give an expression for this affinity that's telling you kind of how close you are to the equilibrium in the system. Anyway, that's mentioned here because it's in the book. Like the chapter on the book on phase stability talks about this. So that's the only reason it's in the notes here, just to kind of cover what's in the book. I'm not sure the affinity, you actually don't see that much. I mean, anyway, maybe you can ignore it. I guess the reaction coordinate, you'll see people talk about the reaction coordinate, kind of having a rough idea in terms of the cyclohexane things. Useful. I mean, it means like you're transitioning from one state to the other. That's, anyway, you've probably seen that before, I guess. But anyway, so the rest of this chapter is about, part of it's about spinel decomposition and nucleation and growth, and the other part is about different crystal states. There's a little bit at the end about different like what's it called? The last thing in here is about this business of polymorphs and allotropes. So you have different crystal structures, and then that has this polymorph allotropes introduces the idea of Oswald ripening. So that's in this chapter too. Anyway, so spinodal is the main thing. So that's why the homework's about spinodal. Anyway, spinodal is kind of a complicated thing. So to start with, so you have the Hildebrand equation for the free energy. So you have the log term, and you have the interaction parameter term, and then so for the phase diagram, if you plot the free energy, so the phase separation point is going to be where the derivative of the free energy with respect to moles of the component equals 0, like the minimum in this curve. Right. And then you can also, there's two other derivatives that are generally done. So the first one is the first derivative of the free energy with respect to composition, gives you it's called the binodal miscibility limits. So from those two, so when that equals, first derivative equals 0, then you have the two phases that are in equilibrium in a phase separated system. It's like x1 and x2 would be like that point and that point if you're at that temperature. The dark line, then single phase above and two phase below. So you cool it down, phase separates into that phase and that phase. And then the spinodal part is a second derivative, it's the inflection point. So at the inflection point, the second derivative equals 0. So basically you can find that's going to be this dashed line. And then the third derivative, so when you reach this point, it's flat, so the first derivative is 0. And it's a point of, the second derivative is also 0 here, and the third derivative is 0 here too. So at the critical point, there's 3 derivatives that are 0. And if you use just the standard Hildebrand equation, that's always going to be at 50% composition. Because let's see, I do the derivatives here. So if you take the Hildebrand equation and then do the first derivative, you end up with this equation. So that defines the binodal. So it defines, if you know XA, you know XB in terms of the Hildebrand interaction parameter. And then if you do the second derivative to find the spinodal, then you can find this equation, which relates XA and XB to the Hildebrand for the spinodal position. So XA, XB is really only one because XA plus XB is 1. So there's only one term. So it's basically, this equation just defines the binodal composition in terms of the Hildebrand parameter and the temperature. And this equation defines the composition of the 2 phases in equilibrium at the spinodal, the two spinodal points in terms of the temperature, same 2 parameters. And this, once you take the third derivative, there's only one solution, XA, XB equals 0.5. So if you take the derivative of this equation with respect to mole fraction, you end up with this equation equals 0. And that doesn't have because this doesn't have a mole fraction, that drops out. You just have the composition if you solve this thing. So you can get rid of RT, 0 over RT 0. Then you basically end up that it has to be 50% for the critical point. And then you can plug that critical point into spinodal, into this equation, and find out that the critical temperature has to be the Hildebrand over 2R. Right? So you could actually go back and substitute in, instead of putting the Hildebrand interaction parameter, you could just put 2RTC here. So you could just write this whole thing in terms of temperatures. Like this critical temperature replaces this interaction parameter. TC times 2R is that thing, right? Just because of the way that has to work. Then that kind of simplifies this. Then your spinodal composition is going to be T over TC. And then the binodal is going to be TC over T times this, right? So basically, once you have that solution, you can solve all the rest of these in terms of this critical temperature. So anyway, that's kind of how things go. So structurally, anyway, so structurally, what happens is that when you're in this region between the spinodal and the binodal, so this is called the binodal. That's a miscibility limit. The spinodal is a point where the curvature of this free energy changes from concave up to concave down, right? And concave down means that you get spontaneous separation. In other words, if you have a fluctuation in the composition, which is here somewhere, here. So if your composition fluctuates somewhere, so temperatures, so the composition's an average composition is fluctuating all over the place, like this picture, like that. So you have this kind of composition fluctuation everywhere going on constantly because KT is driving molecules around. So basically, this kind of fluctuation is going on. That means you have like, and whenever you have an up composition flux, it has to be a down one to compensate it, so you get the average. Right? So that means you can have 2 terms to the change in free energy for fluctuations. You're going to have an up plus the fluctuation and minus the fluctuation. It's like 2 Hildebrand equations, sum together and take half of that, right? And then this is the average one. Well, the difference between the fluctuation free energy, just calculating the Hildebrand equation with the up flux and the down flux and take half, then the average Hildebrand, that deviation tells you if you get a positive change in free energy, which will be opposed, or a negative change, which will happen automatically, right? So that's kind of a complicated way to write it. The basic idea is that when you have the situation, if you have any fluctuation and you have this concave up, fluctuation is always going to lead to more upward trend of the free energy than the other fluctuations. You end up with a net positive increase in the free energy, so you drive back to the original. If you have concave down, the opposite happens. Any fluctuation leads to a drop in the free energy, the average free energy. That means that's going to drive the separation. So in the middle, so before you get to the inflection point in the curve, that was here. Before you get to the inflection point, so if you're in the middle of this, basically it's going to spontaneously decompose. It's called spinodal decomposition. So the phases will just happen. They don't need a nucleation site. So when that happens, this is what it looks like. So you have a fluctuation in composition, and then it just grows. So this involves diffusion of composition uphill. In other words, Fickian diffusion is a downhill diffusion. So you go from a high concentration to a low concentration. So delta C drives Fickian diffusion. It's basically, that's the normal way that things happen. That would be nucleation and growth. So with nucleation and growth, you need a seed usually to form. So you have to have a seed, and the seed is a pure component of whatever's forming. And then you have the average melt around it, and then it's going to deplete when you get to the seed because the seed is actually consuming the material. So the crystal you're growing out of the liquid is consuming the liquid, so you get a depletion near the crystal. So that causes Fickian diffusion and nucleation and growth. Spinodal, because of this thermodynamic, the Hildebrand equation, the second derivative, you have it, and because of the concave down shape of the free energy curve, it'll just decompose automatically. So it's the opposite of Fickian diffusion. It's an uphill diffusion of material. So it's an odd thing, right? I mean, it's not something you wouldn't expect. So it took some time for people to figure out how that works, So this is kind of an open question in thermodynamics of materials. So this guy Kahn was at Caltech, and Hilliard was at MIT, and they at the same time kind of came up with a theory called the Kahn-Hilliard theory. Describes like what's going on in this case, like how this case is just Fick's law. In this case is something different than that. It's where thermodynamics is driving the growth. So the growth is still governed by the transport. So you still have the diffusion coefficient of the materials that governs this, and you have the thermodynamic driving force. Whereas here you just have the kinetics of the growth, right? Now, the depth of the quench is useful, but also here it's Fickian diffusion because you have depletion to zero near the interface. So basically, this is just Fick's law that governs the growth rate. And here, this is governed by both the Hildebrand equation, so the interaction parameter, and also the diffusion coefficient coupled together somehow in a mysterious mathematical way, right? So that's the idea of spinodal. That what spinodal results in is that the fluctuations that you started with, so these kind of concentration fluctuations that exist naturally just grow on the sites where they have a random fluctuation, and the phases are co-continuous. So one feature of this system is that the kind of the pastel blue phase and the black phase. So the black phase is co-continuous, meaning that if it was liquid and I drained it out, it would flow out. Or if the blue phase was liquid, I could pull it out. In other words, that's different than if you have spherical domains in it that are stuck. Like the spherical domains are just isolated and they can't drain, right? So basically, that allows you to do something like this. Like if you go back to this guy, he's trying to make a dental implant, right? And he wants to have it porous so that tissue can grow into it. So he wants to have this kind of porous structure, and he wants to have a gradient in the porous structure. So he wants to have it like porous on the outside and then rigid on the inside so that the thing doesn't break, I guess. So basically he's looking for a gradient. He's trying to get, and so he wants a spinodal structure because it's bicontinuous. so that he can wash out the second phase that forms here. So he has the solid phase and he has some kind of liquid phase or phase that can dissolve in acid or something like that. So then once he dissolves the inner phase, then you can have this porous structure that tissue can go into. Right. So that's the aim here. So that's similar to what was done with Vicor glass, okay, which is kind of spinodal glass structure where you phase separate. So let's see, down, 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 down. Vicor glass is almost very similar to that. So this is a phase diagram for borated silica glass can make, and then you borate it. And the boron phase can be removed if you make a spinodal structure. And so you phase separate. The phase separation curve is here, the liquid-liquid phase separation superposed on the kind of crystal liquid phase diagram. So if you do a deep quench in the middle, you get spinodal. And then with that, you can acid etch it and make this Vicor glass. Vicor glass is a heat, it's a heat insensitive glass, right? Basically, you can take that glass and etch it away and make fused silica, make a filter. You can make a Vicor glass fritted filter that's got kind of sub-micron size pores in it. So it's useful for filtration. I mean, if you want to have a glass filtration, use Vicor filter. And the other option is you make phases that couldn't be dissolved away. So that's the Pyrex separation and nucleation growth. So it's not in the middle of that phase separation point, but and over to the side where you get nucleation. So the spinodal would be between those two somehow. Right. So Pyrex is domains, nucleation growth domains of spheres. Vicor is this web structure bicontinuous. Because it's web structure, you get this filter formed from it. Okay, so that's kind of the model for what this guy's doing in the paper. Anyway, so that's kind of the broader picture of like what's going on with the spinodal. Like you have to know about this derivative thing to figure out where the spinodal is. So the first derivative gives you the binodal, second derivative gives the spinodal. So that's the inflection point in the free energy. And the third derivative gives the critical point, which you can solve directly. You can plug that into the equation, the spinodal, because at the critical, all three apply. And then you get a solution for the critical temperature, which you can plug back into these equations and kind of solve the entire phase diagram, just knowing not just knowing the critical temperature. Okay, so if you know the critical temperature, you know everything else. You can predict all the other parts of the phase diagram. So this kind of simple spinodal phase diagram. So all right, there's a twist to this thing for polymers, right? So again, like it's so Vicor glass and Pyrex, like the classic examples from ceramics. But basically you can't, so the phase size is very small in those. So you can't exactly measure it. So polymers are much larger. So the phase size is correspondingly larger. And the dynamics of polymers is very slow. So it's on a second time scale versus a millisecond time scale. So you can observe the spinodal decomposition in polymers much easier than you can in ceramics and metals. Right. And also it's also observed in like biological systems and things. So it isn't just limited to low molecular weight. Anyway, the difference though is that in polymers, you have this Flory-Huggins equation. Because the molecular weight's high, the entropy of mixing is really small. Right. So the entropy of mixing goes almost to zero. Then you just have this entropy of mixing. So basically it would mean that for a normal case, you would never have, so this usually makes things mix, and this thing makes things demix. So you would never have mixing at all in a polymer because there's no entropic mixing term. So basically this dominates. But there are some polymers, a few that mix. And that's because this interaction parameter has both a so this interaction parameter, so I've removed T out here. So this thing has to be omega divided by t. So anyway, omega is going to be this a minus a plus b. So the t term here is actually the enthalpy term, and the a term is the is an entropic kind of term. So basically, there's some kind of ordering that happens in the system when it's that drives the phase separation of the system, so that you lose entropy because the system orders. It's not this combinatorial entropy, it's a non-combinatorial. It has to do with the ordering of the components. So you end up with a more complicated interaction parameter. It's got a plus and a minus term. This term goes to almost zero. And basically it's a balance between these two. And what happens is the temperature goes up, the thing becomes immiscible. So this term, so the negative term means it's going to mix, and the positive means it's going to demix, because you're dropping the free energy for the negative term, you're increasing the free energy of the positive. So when you get a high temperature, the system demixes. So the normal state of affairs for a polymer, because you have not much entropy of mixing, is that it phase separates on heating instead of cooling. So it's called a lower critical solution temperature, because the critical point's at the bottom of this curve. For a normal system, the critical point's on the top like this. So that's called an upper critical solution temperature. This is called a lower critical solution temperature. And this occurs because you have no entropy of mixing, and because you have a non-combinatorial entropy term. And this is driving the mixing. There's just an ordering that happens when it mixes that reduces the entropy. So anyway, so that's the twist of this. So a lot of the literature about spinel decomposition is going to be using phase diagrams like this that are upside down of this. That causes some confusion. Right? In other words, you're heating it up to phase separate, which is an odd thing. And anyway, that happens. It's polymers, and that's kind of how polymers are. Because the molecular weight drops the entropy of mixing, because it's all basically one giant molecule. So there's no things that are mixing. So anyway, in polymers, so they're going to plot, like, instead of plotting, so chi, because if you remove temperature from it, chi is going to have, so the omega, so chi is omega by t, so chi has a 1 over t dependence. So instead of plotting t, people will plot chi. So this axis would really be 1 over t. Right. So this is showing an upper critical solution temperature, because high chi is low t, so it's phase separating on reducing the temperature. So even though this is a polymer thing, they're showing it for kind of a ceramics kind of phase separation on heat, on cooling. Chi is 1 over t, so this is an inverse axis in these plots. But you'll see that plot in some of the papers for this. So there's that business. Anyway, this is kind of, so in polymers, you can actually take micrographs of the spinel structure from it, which you can't do in metals and in ceramics. So basically, it's going to look, this is a spinodal, this is a nucleation and growth kind of separation. So they're distinctive. So the odd thing in this is that it looks like a mess. So it doesn't look like there's any order to this. But in fact, because it's the fluctuations that were in the system originally, and they've been grown along the lines of the original fluctuations. And those are determined by basically the diffusion coefficient and the distance that you are from the phase separation point. So in other words, the depth of quench to get the phase separation and the transport properties of the molecules. So those two things have to balance out, and they balance out in a perfect way. So the separation distance between these phases and the size of the phases is the same, roughly the same throughout the whole thing. So because you have like a perfect size, that gives rise to like if you do a correlation function on this, so you take a point here, then how far am I until I get to another of the blob phase, right? So that's got a fixed distance on this. That means if you plot the correlation function, it's going to have a peak in it. And when you the Fourier transform of the correlation function is the light scattering. This is on a 10 micron size, so it's light scattering. You look at it, like the spacing between these is 10 micron. So basically, if you shoot a laser beam through this, you get a ring that has this a correlation that reflects the fact that this thing has a fixed size in it. So the correlation function has a peak in it. The Fourier transform of the correlation function gives a peak in the scattering curve, the scattered intensity. So you get this kind of ring. So this is a setup where you've shot a beam of light through a sample, and then you have a sheet of paper on the end. Then basically you'll see this ring if it's spinodal. And as time goes by, so if you let the thing phase separate and watch it with time, the ring slowly collapses down towards the middle. So you get a smaller and smaller angle, which means you get a larger and larger phase size. So basically this collapsing peak is called, they relate that to Ostwald ripening of this structure. So this is a picture of what's going on. A, B, C, D. So you kind of, basically, the phase size gets larger as you go along. Then finally the large phases will eat up the small ones. You end up with just domains that look very similar to nucleation and growth. So if you wait long enough with spinodal, this peak will collapse down to zero. You just have these domains left. It looks just like nucleation and growth in the end. Right? I mean, you can, if you quench the thing, if it's a thing that will turn to glass, matrix could turn to glass, and you can quench it and lock this in. If not, it's just going to nucleation and growth, and spinodal will just look the same in the end, because it'll just decompose into these same kind of domains. So people have studied that quite a bit. These are micrographs showing that this is like 100 micron scale bar, so it's about 10 micron spacing of the phases in this. Anyway, so it ends up, so that's kind of like the simple, even though it sounds complicated, version of this, because it basically, the way Con Hilliard did this, they talked about this 3D, like a 3D transport thing. Okay, so this is a Con Hilliard equation. This would be the Helmholtz free energy. So you can think of this as G, like the free energy of the system. And it's composed of this would be the Hildebrand equation, small f, or the Flory-Huggins equation for miscibility. And they add in this other term that has kappa, and kappa is the effect of this concentration gradient that spontaneously forms. Right, so this is like driving the phase separation, and kappa. So kappa ends up being related to the transport of the thing, like this gradient's forming because of the transport issues in this. And this is a del C. Del C is the gradient, like how much concentration gradient, like the slope of this curve. Right. So the slope of the curve squared times this kappa, so the weighting factor for that. And then the free energy. So that's basically the Con Hilliard equation. In the paper, if they give this equation in the paper, the simplest place to look at this is a polymer guy, this Hashimoto, and he spells out exactly how to apply Con Hilliard theory to look at this kind of light scattering measurement, like this kind of measurement of time. Right. So basically, that's the simplest way to study it, is to look at the light scattering, and the light scattering. So you see this Q. So Q is like the angle. It's kind of the center from here to there would be the angle. So you're coming in with a beam this way, and then the angle of scattering is like kind of that distance. Right. So basically, Q is sine of that angle. So 4 pi over the wavelength times sine of that angle, or sine of half of that angle. So that means that's basically Bragg's law. So Q is 2 pi over the spacing of the system. So Q is 2 pi over whatever the separation spacing of this system is. So if you get a low Q, 2 pi over the spacing means a large size. And 2 pi over this spacing, you mean a small size. So it goes small to large as you go down. So this is called inverse space. It's inverse centimeters. It's like basically you're looking at small and small size. The Q is called the wave vector. It's called the scattering vector. It's got a bunch of different names, but basically it's Q. Sometimes it's S, usually Q. In this case, it's going to be Q. So it's basically, and the Q star is like where the peak is. So 2 pi over Q star would be exactly like that average spacing between these phases. Right. So anyway, so he's looking at it in what they call Q space or inverse space. So all this analysis is going to be in terms of like Q. Q would be 2 pi over a size, the size of those phase separating things. And this RQ would be the rate of growth, like how fast does that peak in intensity grow over time. So if you measure the intensity at any value of Q, it increases with time as a phase separation happens. So that's the rate of growth of these domains. So you can measure the rate of growth of those domains just by kind of taking a fixed Q, and then this would be the equation that governs that. And basically it's going to give you a, this is the Hildebrand equation or the Flory-Huggins equation, the second derivative of it. And then this is this gradient term times Q squared. So basically from that, you'll end up that you have an exponential, this kind of an exponential growth rate in time. This R of Q, the rate, is RQ times time. Exponential of that gives you the concentration growth rate. So Cahn-Hilliard gives you this kind of, that you should get an exponential growth rate in the phases as a phase separation happens. And so if you plot log of the concentration difference that you can measure from scattering versus time, you should get a straight line. If it's following Cahn-Hilliard's, this is like, this is like a log scale of the intensity versus time. From the slope of that, you can get this RQ, the growth rate term. So looking at one position, so you take, this is the growth of the intensity in Q. So you take one position in Q and just map the intensity growth. So that's the intensity growth for one Q. And you list the different Qs here, right? So it's going to have different RQ. R is going to be, the growth rate is going to be a function of Q. You're going to have a Q where you have the maximum growth rate in the phase. So Cahn-Hilliard theory can tell you what that Q would be. So it can tell you what the maximum Q is, and it can tell you, so there's some Q where the growth doesn't happen anymore. So you can go out, because you get to too small, so you're getting smaller and smaller sizes, some size where you don't get growth of the phase. There's a maximum and there's a zero cutoff here. You can calculate both of those positions from Cahn-Hilliard theory just using the one Flory, using two numbers, the diffusion coefficient, the polymer, and the Flory-Krigbaum, the Flory-Huggins interaction parameter, or the Hildebrand interaction. So you have two numbers. You can kind of predict this whole set of curves for how that growth happens. So for that reason, people are like excited about spinel decomposition, because you can do like physicsy stuff with it. Like you can predict the whole thing from just some simple light scattering measurements, and it works. So that they didn't win the Nobel Prize for this, but basically they got equivalent of that in terms of recognition, I think. So in other words, it's a popular item. Anything that looks kind of messy like that, that can result in like a perfect structure, like a scattering peak, people are interested in it. So it's mathematically, it's kind of challenging if you look at the details, but we don't need to really look at the details. Basically, this is the Flory-Krigbaum. This is the Cahn-Hilliard equation. And then the application of it is in these papers by Hashimoto, with this Spinol 83 paper, kind of goes through the whole thing. I think he pretty much describes everything about it that you need to know. it's difficult. It's not like a simple paper, but basically this is basically all you need to know about it, I think. I mean, it's written in terms of Flory-Huggins equation instead of Hildebrand. So I'll go through these other things next time, I guess. But so maybe that's all I want to say about spinodal, I guess. Nucleation growth. Oh, this just shows. Well, this is a plot from. So this light scattering, you can also say like. So if you have random scattering system, then you say that the kind of a diffusion pathway would be like the distance traveled squared goes with time or something. So you end up with this distance squared is like a parameter that you're looking at for a random system. And if you look at as you phase separate, the intensity increases. So at the initial point of phase separation, 1 over the intensity decreases. So if you plot 1 over the intensity versus this squared size, you can extrapolate down to 0 and get the critical size from that, like the critical phase size that it's going to grow to, and then watching that intensity change with time, with temperature. So you can plot that intensity versus 1 over T, you can get the critical temperature from that plot. So it'll give you like the critical point for the system, like where it phase separates. Not sure why this is stuffed in here. This you don't necessarily need for this spinodal stuff. That's just critical scattering. High core, Pyrex. So what's the other thing here? The only other thing, so I'm going to leave the spinodal with that. It's probably good enough. The other thing in here is this idea of like the nucleation and growth. So so the activation barrier thing. So basically there's 2 kinds of nucleation and growth that you can get here. Let's see. No, that slide, I want the one, that slide is repeated here. So anyway, so homogeneous and heterogeneous nucleation, that's kind of the issue. Right, so heterogeneous, so anytime you have the material, it's got dust in it. So those dust particles can act as a nucleation site. So you don't need to form this brick in the middle. Like that brick is a hair, or it's some dust, or it's anything that's in the material. So that'll act as a nucleation site, and then your phase will just grow on the surface of that. All right, so we'll go through the surface. There's a chapter just on surface, right? So in that section, we'll just go through like that business mostly. This surfaces. So actually, it's the next section, surfaces. Right. So, okay, so we'll go through this thing in some detail there. But basically, for here, since we're talking about nucleation and growth versus spinodal, so basically, this is kind of in a nutshell what's going on with this. So you could have a heterogeneous nucleation, which would just be dust, and then these equations wouldn't apply. But say you had an absolutely perfectly clean system. So within spinodal, the dust doesn't matter because the phases just spontaneously decompose. But if you're doing nucleation and growth, the dust matters because you need to have a nucleation site in order to grow, because you're in the frown part of the phase diagram. Right? So it doesn't spontaneously decompose. It has to have nucleation sites. So anyway, so that's heterogeneous nucleation would be the dust. You can also have homogeneous nucleation for nucleation and growth, and that's kind of a spontaneous growth, even though it's a non-spontaneous system, right? So in that case, if you're getting homogeneous nucleation, you consider what kind of phase size would grow. So you write the free energy this way. So you're going to include the surface energy, which is why it's the next chapter. So the surface energy of the phase you're growing times r squared. And then the volumetric, which is the thing we've been dealing with all along. So this is the Hildebrand equation for the delta G. And then you have to add in a surface term, this r squared times sigma. So you have two terms, right? And then, so basically from that, you can get, so if you find out, so if you look at this thing and you plot that free energy as a function of particle size or domain size that you're growing, so as r increases, this negative free energy of formation from the Hildebrand equation, in other words, it wants to decompose, so you have a negative term, so that's going to drive the high r size. So when you get to large phase sizes, then you get growth of phases. Right? So the cutoff point here is 0. So if you have dust in there that's larger than that cutoff point, then that will grow a phase automatically because you have a negative delta G to form the phase. Right? On the other side, it's positive, but there's a maximum in it because as you get smaller, then the sigma term starts to dominate, which is positive because it's r cubed, r squared. So it's small r squared can start to dominate, and then you get this positive contribution to it. Anyway, so there's a peak because this curve has two terms that have different dependence on r. Right? So taking the derivative of that, you can solve for what the peak is. That gives you an energy for nucleation, like a nucleation barrier energy. Once you get above that energy, then you spontaneously form. So once you get above that energy, you spontaneously form. So I recorded on Zoom. So right. All right. Right. Anyway, so if you get above that energy, you spontaneously form, and then basically that energy barrier decides the rate of nucleation that you're going to have in the system. Right. So you have, see, from the derivative of this, you get that peak. Once you have that, right, once you get that size for the peak, you plug it into this equation, you can get this barrier energy. If you plug that in, you can get the nucleation rate for the system. That's going to decide how you can form, how nucleation growth is going to happen in a homogeneous setup. So anyway. I don't know, why don't we just quit there? I guess that's it for today. I think I'm just gonna, I can finish this. There's a couple slides left on this, but I can finish it later on. So I'm just, that's it, I think, for today.